So question 3, this was taken right out of the textbook, and I wanted to include it in the assignment because this is a question that's a little bit more suited to clarifying a little bit of the math sort of language and notation, and to try and understand it better. This starts off by saying the change in Gibbs energy. So in other words, the delta G of a constant pressure process was found to follow this. So the delta G versus T was like a straight line relationship. But they want you to calculate the value of delta S for this process. Now, what I used to realize is sometimes in physics and PChem, as soon as you see an expression like this, that it was where something was a function of T, it normally made me think I'm probably going to have to either integrate this with respect to T, or perhaps take the derivative of this with respect to T. So even if I had no idea what it meant, it's making me think I'd probably do either integrate it or take the derivative, just if I'm guessing and I had no idea. So, but let's take a close look at how this is going. Turns out that in this textbook, that's question 3. There's a specific relationship, partial derivative, that looks like that. Now, what this is literally the rise and run. It's the slope of a graph of G versus T. So if I was like Mother Nature and I knew the exact value of G itself, as opposed to knowing a delta G of a reaction, I know the exact value of G for a substance. This is a constant pressure process. So imagine you have a gas, and as the temperature changes, the exact value of G, which Mother Nature knows, would be known. You watch what it does. The slope of this graph is equal to negative entropy. So the slope of the graph, so it's almost like, I mean, I'm just going to draw, not the one for this question, but let's just say it looked like this. So imagine at one temperature versus another temperature. The slope here versus here. If it was straight line. But what if you had some other graph? This is just examples. I'm making them up. What if you had a different one where you had at T1 and here at T2? Well, now that I have a curve, if that's what it looked like, it's the slope at these points. Well, it turns out that the slope would be the entropy at part 2, and this would be the slope at the entropy at part 1. If the relationship between G and T happened to be straight, do you see how the slope on a straight line is the same? So this one would tell me that the slope here and the slope here, S2 minus S1, would equal 0, because the slope is the same. Now, normally, when you change the temperature of a gas, it stands to reason that you should have, if I increase the temperature, it would almost make sense that the entropy should go up. So maybe I drew this incorrectly, right? Maybe it's more like this. You know, the slope down here versus the slope here, right? So you get the idea. This tells us that the exact value of entropy is the slope at values of T of this graph, whatever the heck it looked like. So that's the idea. So the one thing I know is if you're asking a process takes place, in this case, the change in entropy will be S2 minus S1. So now instead of thinking about the graph, which gives us some meaning of that one, now we're going to say algebraically what would happen if I looked at delta S. So S2 would be the value of G2 Now what's interesting is, here I was showing two different temperatures. Yeah, what's interesting is, this is saying it's understood that the way they algebraically come up with this is to get S, the negative goes over here. So it's like you're saying the negative of that one minus the negative of that one. G2 I'm going to factor out this negative. See that negative? I'm going to factor it out. So now, and the interesting thing here is, folks, which I'm gonna have to come back to this. Why would I not put a T2 here and a T1 there? I think I just answered my question. Think about it. The entropy is how G is changing at a given temperature. And by default, I don't even necessarily have to draw that in. But the point is, if I take the slope at one point of the graph and the slope of another, you can see how there is a delta G. There is a delta T. But it's almost like you're saying you're taking the derivative at one point of the graph versus another point, and it's that difference in those two values. It's a difference in the slopes at two different points. I mean, you could even put that in, and that's fine. How is G changing as temperature at the point 2? So what is the infinitesimal slope at that point? So you can write this in, and that's fine. But what this works out to be is, how are you changing? No, we'll have to take that out, and I'll come back to it. Like I said, I'm still not 100% sure. What I do know is this. You can go from, when you have something like this be the slope of a graph at 2 points, you are allowed to look at the second value of G minus the first value of G, and because you are taking the derivative with respect to T, you're allowed to do this. I'm not 100% sure the mathematical exact reason why, but long story short, what this tells you is when the pressure is constant, you take the derivative of G. If somebody gives you delta G as a function of T, you take the derivative of it with respect to T, and that will give you the change in entropy. So one of the corollaries of this, folks, what I'm getting at is, you're given this. So one of the corollaries is to say you are allowed in the numerator to put a delta in front of that. And put a delta in that one. Yeah. And there's a reason somewhere within this that this is your slope. This is changes in the slopes at the two different points on a G versus T graph. So if someone finds that the delta G is a function of T, you can take the derivative with respect to T and it will give you the delta S of the reaction. So long story short, I think this shows you what you want to do. You have an expression right here, so you're going to take the derivative of 85.40 plus 36.5t. And it's told this negative we'll put over here. Take the derivative with respect to t. So when you take the derivative of this, I mean, I think you can see what you're going to get here. That'll give you your answer when you carry that out. So that would be for number 3.